Hey, hello everybody. So today we're doing some supplemental work on section 7.2 and 7.3, trig integrals and trig substitutions. We have 4 problems that we'll be working through. So let's jump right into it. So our first problem, we have integral sine cubed of x dx. This is kind of a warm-up. We've seen problems similar to this before. And if you remember, the key idea here was that we had the integral of a trig function to an odd power. So we have integral of sines and cosines where the total number of powers is odd. And the technique that we used there was to break off one of the trig functions. Leaving us with an even power left over. And by making this our du, reverse engineering what we need to make u to make that happen, we can either directly transform the even powers that are left over into u's, or if we need to, we can use Pythagorean identity to transform the sine squareds into cos squareds or the cos squareds into sine squareds, and then be able to translate them directly into u's. So if I want sine x dx to be du, I want u equals cos x, which will make du equals negative sine x. So this will end up being negative du in this setup. We see that this is going to be equal to integral of sine squared x. Doesn't convert nicely into u, so we'll do a little bit of work on that. We want to rephrase sine squared x in terms of cosine x. So we have 1 minus cos squared x from Pythagorean identity. And then we have a negative du. This negative here is going to just swap these two terms. And we end up with integral of u squared minus 1 du. This is, of course, 1/3 u cubed minus u plus c. And I suppose we could end it here, but we really always want to translate everything back into the original variable that the question was asked in. So we really should go one step further and say that this is 1/3 cos cubed x minus cos x plus c. One thing that we're going to find useful as we kind of go deeper into integration techniques is this idea of, kind of morally speaking, does the answer make sense? So just as kind of a general observation, we kind of have an idea of how trig functions tend to integrate. We integrate a trig function, we tend to get a similar trig function back. So does it kind of morally speaking make sense that the integral of sine cubed would basically have a dominant term of cos cubed? And I think that kind of does make sense, right? Sines kind of translate to cosines, cosines to sines. So that kind of seems like a sensible thing to get out of the other end, right? If we ended up getting a square root of x out or something, we might be a little suspicious. But this seems kind of in line with what we might expect. Obviously, that's not a rigorous or a technical statement, but it's just, it's kind of a way for us to check a little bit whether we think, after we do all of this complicated work, whether we think the answer we got maybe is somewhat reasonable, or maybe we're a little suspicious and we want to check a little more carefully, go back through our work and make sure we didn't make a mistake. Okay, the next example 2 here. Here we have alternating current and voltage in a circuit. It's described by this sinusoidal. So a nice, maybe a typical type of voltage that might come out of your wall socket in your house. Has a peak voltage of 170 volts, and the frequency is 60 hertz. So kind of a typical American household, voltage description. And we'd like to find the RMS, the root mean square voltage, that's described by this expression over here. And the important part that we're going to try to find is the integral of v squared. So that's where this relates into trig integrals. Why do we want to find the RMS? Why do we care about this big complicated expression? Kind of roughly speaking, this is saying this is related to the amount of power, the amount of work that you can do from that electrical current. So kind of what this is saying is, for an alternating current, sometimes I have a lot of voltage in one direction or in the other direction, but sometimes I have very little voltage, right? So I have periods where I have very little electrical potential and other periods where I have a lot. If I'm running a light bulb or something, I don't really see it fading in and out because this goes up and down, 60 times a second. But there is some variability there. So I might want to ask the question, well, suppose that I, use this AC electricity to, say, charge up a battery, and then I use that battery to output DC, direct current. What would be the kind of equivalent voltage that I would, that would come out of that battery for that amount of time? That's kind of the idea that we're getting at here. I'm not a physics professor, so don't hold me to all of these minor details, but that's roughly the idea. That's why we care about this root mean square voltage. It's kind of the right way to average the voltage function so that we can get a meaningful description of things like how much work can we do with this current. Okay, so we see that the important part here is this integral. We need to choose an interval AB, and since it's a 60 hertz function, the one cycle of the function goes from 0 seconds to 1/60th of a second. The reasonable time interval to use might be 0 to 1/60th. This will get us one cycle, right? If we're averaging, it's probably sensible to pick a single cycle to average over. I wouldn't want to pick, like, say 1 1/4 cycles or something like that. My drawing's a little bit off, but I wouldn't want to pick some strange number of cycles to average over, because then that's going to throw off my average a little bit. But if I average over just one cycle of this trig function from t equals 0 to 1/60th, I should get a sensible average. Okay, I probably could even get away with 0 to 1/120th, or maybe even 0 to 1/240th, because of all the nice symmetry, but we'll just kind of make it easy. We'll take just a single full cycle. So let's compute v squared RMS, just so I don't have to keep writing the square root. Then we'll square root at the end. So I see 1 over b minus a. Well, b minus a is 1/60th. 1 over that is 60. So that's this fraction out in front. And then I'm integrating from 0 to 1/60th. I'm integrating v squared, which is 170 squared sine squared 120 pi t dt. So I see I can pull these constants out. I'm just going to call these constants k, so I don't have to keep writing them. So here k is, what is it, 60 times 170 squared. Okay, so I need to integrate a sine squared. So unlike the example 1, here we have a total number of powers of 2. We have an even number of powers. So if I tried something like breaking off a sine to make a du, then my u would be like a cosine, but it's going to be hard to switch a single cosine into a single sine, right? Pythagorean identity doesn't work so nicely there. So what's the other approach here? The other approach we talked about when we have an even total number of powers is to use our half angle identities. So we note that sine squared of, let's call it theta, is 1/2 1 minus cos of 2 theta. So we had this identity that we can use. We can switch the sine squared into this other expression that has a cosine to the first, which we can essentially directly integrate. So k comes along for the ride. We are maintaining our same variable. So we're not doing a substitution or anything like that. So we can keep our same bounds. Sine squared of stuff becomes 1/2 1 minus cos of twice that stuff. So we'll say that's 240 pi t dt. That's a 4 over there. Let me see if I can. Outlook loves to change my 4s into 9s. 240 pi t dt. Okay, so we end up with what? K over 2. And then integrating this with respect to t gives me a t minus cosine integrates to sine of stuff. Now I integrated to sine, but if I differentiate, sine differentiates to cosine, but then I get a 240 pi that pops out. So I need a 1 over 240 pi. And here t is going from 0 to 1/60th. So we get k over 2 times, we get 1/60th minus 0 from the contribution from t. Subtract. So let's see, sine of 0 for the second bit is going to be 0. 1/60th times 240 is 4. So that's going to give me sine of 4 pi. But sine of an integer multiple of pi is 0. So this is all going to net out to 0. All of this contribution from the sine of 240 pi t nets out to 0. So I get k over 2 times 1/60th. Now what was k? That was 60 times 170 squared over 60 times 2. My 60s go away. I get 170 squared over 2. So I see that I have my max voltage, my V max, 170. That gets squared and then divided by 2. The over 2 came from our half angle identity. So that stuck around. But this 60 hertz kind of divided out. That seems kind of reasonable, right? That this 60 that we got was from the interval that we chose. So I wouldn't expect 60s to be left floating around, right? If I had a 60 floating around, then if I had chosen, 2 cycles or 5 cycles or 10 cycles, that would be a different number. And that doesn't seem right. So I should, if I'm averaging over reasonable cycle lengths, I should always get the same average voltage. So we do see those 60s divide out. We do see this is the squared VRMS. And we see that we get voltage squared. So the units are right? Square volts and square volts. So again, some of these checks that you can do to, just get an idea of whether you think the result that you got is reasonable. So this tells me V RMS is 170 over √2. And this is a general formula for this kind of a voltage. For a sinusoidal voltage is VRMS is going to be V max over √2. And this turns out to be about 110 volts. Let me call it volts, since we kind of already used the letter V. So our RMS voltage coming out of our wall socket in a typical US household is going to be 110 volts at 60 hertz. And sometimes they say 120, and in reality, power plants and power distribution isn't perfect. So it's going to be somewhere in the ballpark of 110-ish, maybe 115, maybe 120. But as long as it's not too far away from that, things are going to just work just fine. Okay, so the next example, find the volume enclosed by the torus created by rotating the following region about the y-axis, and I'll draw the region now. So we have a region that is a circle. The circle is centered at the point capital R, comma 0. And the circle has radius little r. We're rotating this region, this circular region, about the y-axis. So this is our x and y axes. So we can see this is going to rotate around and make a torus or a donut. We note that there are two radii that we have to consider here. There's like the radius that represents kind of the thickness of the donut, and then the radius that represents kind of the width of the donut in, you know, some manner of speaking. So that's little r and capital R respectively. So what's my torus going to look like? It's going to look like this. I'm probably not going to be able to draw this too well. It's a little hard to draw these kinds of things on a screen like this, but I might be able to get the point across. So it's going to be kind of a donut like that. All right, so what can we do here? Well, let's use cylindrical shells. So what is the volume? Well, the volume is going to be the integral. So we have 2 pi x, where x represents that radius of the shell, times f of x, where f of x represents the height of the shell. So what is f of x going to be? What's the height of a given shell going to be? Well, my function here is going to be x minus big R squared plus y squared, because my center is at big R, comma 0, equals little r squared, because that's my radius for the circle. Or this tells me that y is plus or minus root. And what's it going to be? Little r squared minus x minus big R squared. So that's my y, and the plus is going to represent the top half and the minus the bottom half. And so I see that the height of this shell is going to be top half minus bottom half, but that's plus minus a negative of the same thing. So that's just twice the square root. Okay, and that is dx. And then I also have to figure out my bounds going from here to here. I note that this left bound on x is going to be at the x value, capital R minus little r. So capital R minus the smaller radius. And the value over here to the right is going to be a capital R plus little r. So this is the integral I need to do. This does look kind of promising to do. It looks like I might be able to do some substitutions or something. I do have kind of an x squared inside of a square root and an x outside. So let's work on this. What's the first thing we can do? Well, I think the first thing we can do, we have all of these like capital R's and things and x minus R's floating around. Let's try to simplify that. Let's just, you know, get rid of some of the complexity that doesn't need to be here. So if I have u equals x minus capital R, so setting u equal to this, just to make things a little simpler, du then is just going to be dx. I am doing a change of variables here, so I'll have to revisit my coordinates, my upper and lower bounds. So I have 2 pi. What's x? X is going to be u plus capital R. I have another 2. I have little r squared minus u squared now. Dx is just du. And my bounds, where do they go from and to? Well, u is x minus capital R. So I just knock my capital R's off of here and I get minus little r to plus little r. And if I pull some constants out front, 4 pi integral minus r to r, I got u plus big R times the square root du. I'll switch back to black now. And I'm going to break this into 2 integrals. I'm going to distribute the square root into the u plus r binomial. So I have this integral plus that integral. All right, so something we haven't mentioned in this course, but should have come up in Calc 1, is the idea of symmetry, the idea of a symmetric function. So we can have even versus odd functions. If you don't remember this, take a look back at some of the Calc 1 material at even and odd functions. And we can really make use of this symmetry in integrals, because if we integrate a symmetric function over a symmetric region, we can tell a lot about it. In fact, this is an odd function, odd in u, integrated over a symmetric region. And integrating an odd function over a symmetric region, provided the function is integrable, which this is, that integral is 0. Essentially, when we're to the left of the y-axis, we get the opposite sign of when we're to the right of the y-axis, and the areas are equal in magnitude, so they exactly cancel out. Now, for an even function like this, the u comes in only as a u squared, so the sign is squared away. Integrating an even function over a symmetric interval, we just get twice the integral over one side of the interval of integration. So what does this boil down to? I still have my 4 pi out front. This whole integral went away. That whole thing is 0. I have a capital R. Then I have twice the integral from 0 to plus r. That just makes it a little easier to do later on, a little easier to plug some of our variables in and figure out what our new bounds are going to be and so on. Nothing changed as far as the integrand is concerned. And we can make this an 8. Okay, so we're now down to a single integral to do. And we note that this is the type of integral that a trig substitution might work well for. A standard substitution, something like, s equals r squared minus u squared, that fails because ds has a u du, and we don't see any factors of u that we can use to help us out there. But a trig substitution, so say letting, what do we want to do? We want to let u equals r times sine of theta. So that might be the idea here. Why do we do this? Well, we note that u squared is r squared sine squared theta. We have r squared minus r squared sine squared theta. which is r squared times 1 minus sine squared theta is cos squared theta. So that's what r squared minus u squared is equal to. And when I square root this, I just get r cosine theta. So I have an r cos theta coming from there. I have to be very careful. It's tempting to just, do d theta or something like that, but really I have du here. And du is going to be r cos theta d theta. So I get another r cos theta d theta. And I have to be careful about my bounds. When u is 0, well, we can pick theta equals 0. And when u is r, that's when sine theta is 1. So we'll do pi over 2 for that. I suppose maybe you could have picked different values for theta there because of the symmetry of the trig function, but these are definitely the way that I'd recommend proceeding. Okay, so I see that I have 2 factors of little r that are going to pop out. This is kind of looking good because our radii, both big and little r, would be in units of distance, and volume should be units of distance cubed. So that's kind of looking promising that I have big R times little r squared, that's cubic units of distance. Then I have to integrate cos squared theta d theta, that should be unitless. So it seems like my units are going to work out okay. So that's a good indication. And once again, we're integrating a trig function or sines and cosines where we have a total number of powers that are even. And with these even powers, I'm going to use my half angle identity. So cos squared of theta becomes 1/2 times 1 plus cos of 2 theta d theta. This 1/2 pops out and makes a 4. And then I have a theta plus when I integrate cosine, it integrates to sine 2 theta and 1/2 from 0 to pi over 2. Once again, my sine contributes nothing. Sine of 2 pi over 2 is sine of pi is 0. Sine of 0 is 0. When I put in 0 for theta, that contributes nothing. So the only non-zero contribution I get is when I plug pi over 2 in for theta. So the pi hits that pi, the 4 gets divided by 2, and I get 2 pi squared, big R, little r squared. And as I mentioned, the unit seems sensible, so that's at least an indication that this the answer that we got is a reasonable one. Okay, and our last example here, we're going to see that this is a fairly involved example. There's going to be a lot of different techniques, and this is going to be actually kind of a nice review of several different integration techniques. Despite seemingly looking, not too difficult, this is going to be a challenging problem. So we might actually notice that this looks a little bit like this integral up here, which wasn't all that difficult to do, but the minus is replaced by a plus. So our trig substitution is going to be different. A sine or a cosine isn't going to really work here. We're going to have to do something different. And we'll jump right into it. Our trig substitution is going to be a tangent, because 1 plus tangent squared equals secant squared, and when we square root that, we get secant out. So that lets us get rid of the square root. For this problem, we're really going to be looking at simplifying kind of one step at a time. We're just looking at, we have a problem, we have the complicated stuff under a square root. Can I just get rid of the square root? And then I might have another problem, and I'll look at, can I get one step further? Can I get one step simpler? I do this a few times, and before I know it, I'll be at the answer. Okay, so x equal tan theta doesn't quite work because that gives me 1 plus 3 tan squared. So I need, when I square x, I need a 3 in the denominator. So I need a x equals 1 over root 3 tan theta. So what does this tell me now? X squared is 1/3 tan squared theta, which says 1 plus 3x squared is, so 3x squared, the 3's go away, 1 plus tan squared theta is secant squared theta by the Pythagorean identity. Okay, so that looks good. Let me also write my dx so I don't mistakenly just make that dx a d theta, an easy mistake to make. The derivative of tangent is secant squared. So if you're not up to date on some of your derivatives of trig functions other than sine and cosine, it might be good to just kind of quickly review those. 1 over square root of 3. And this integral then turns into what? It turns into the square root of 1 plus 3x squared turns into just the secant of theta. So we reduce that complexity. We're happy there. We have some extra complexity that came out of the dx though. So we'll have to deal with that now. 1 over root 3 secant squared theta d theta. So I could look at this and say, okay, well, this is like an integral of secant cubed theta d theta. I don't really have a good idea of where I can go from there though. Right, just kind of a direct attack with a substitution or something doesn't work, because for sines and cosines, the nice thing is derivative of sine is cosine and derivative of cosine more or less is sine. But derivative of secant is not something nice. It's not like a tangent or something, it's secant tangent. So that's kind of troublesome. So just trying to, pick like du equals secant theta d theta, what's u going to be? That's not so obvious. Okay, so we need a different approach here. So one thing that we kind of might notice is that the derivative of tangent is secant squared. That's how we got this secant squared in the first place. And so we can integrate secant squared theta d theta, and we can differentiate secant theta. The derivative of secant theta is secant theta tangent theta. So this is not something that, you would likely decide to go on this path, after 15 seconds of looking at this problem, your first time seeing it. This requires, a little bit of thought, some trial and error. You might try a couple of things, try a couple of substitutions, maybe try a Pythagorean identity or something, and maybe eventually land on this idea of doing an integration by parts. When you recognize that you can integrate this and you can differentiate that, and you get some things that look maybe a little bit simpler. So what do I want to differentiate? I want to differentiate secant theta, and I want to integrate secant squared theta d theta. The derivative of secant is secant tangent. And the integral of secant squared, the thing that differentiates the secant squared theta d theta, is tangent theta. Okay, so our integration and we have the 1 over root 3 that will carry along with everything. So our integration by parts says that this is going to be uv minus the integral v du. So that's going to be secant theta tangent squared theta d theta. Now, something that we might notice here is that Secant theta, maybe there's not a whole lot I can do with that, but tangent squared, well, tangent squared participates in this nice Pythagorean identity with secant squared. So tangent squared is going to kind of look like a secant squared. So if tangent squared looks like a secant squared, this is going to seemingly look something like a secant cubed. And that was what I started with up here, was a secant cubed. So maybe I can get something like integral equals stuff plus integral, and then solve for the integral. That example that we did at the end of the last supplemental problem or supplemental video. All right, so let me try to switch this integral into all secants. Okay, so I have integral of secant squared tangent squared d theta. So I'm going to use my Pythagorean identity here, and I note that sorry about that break. So again, we're going to try to switch this tangent squared theta into a secant squared theta and try to solve for our integral. So what's that going to look like? Well, we have, as we saw up here, 1 plus tan squared theta is secant squared theta. So tan squared theta is secant squared theta minus 1. So we're going to use that. There's a lot going on here, so I will keep rewriting all of my details so that I just don't lose track of them. So tan squared, so 1 plus tan squared is secant squared is secant squared minus 1. Now I can distribute and split my integrals apart. And then I have a plus this integral. And what do I see? I see if I call my first integral I, so that will be 1 over root 3 integral of secant cubed theta d theta. I see that that's equal to 1 over root 3 secant tan minus, well, this is that exact same integral. Now, unfortunately, we have this other integral that pops up, but we can deal with that in a second here. But the main thing that I see is that I'm going to be able to get rid of my secant cubes. So this will hopefully make things a little bit simpler still, right? Just chipping away at it a little bit at a time. So the answer all the way up here, the answer to this is the integral that I'm calling I. So if I find I found the answer. It's good to kind of keep track of what all of our variables represent. That's the answer to the problem. But I note that 2I equals this stuff on the right-hand side, the secant tangent, plus this integral of secant, or 2 root 3I. Let's go that route so I can stop writing all these root 3's. 2 root 3I equals secant theta tangent theta plus, so I multiplied by the root 3, so I just need integral secant theta d theta. So I'm almost there. I just need to integrate secant theta d theta, divide by 2 root 3, and then switch back into the x world. Okay, so let's I'll leave myself a little room and then I'll come down here to integrate secant theta d theta. And unfortunately, this isn't a trivial integral to do either. Right? We might try some things like making it a 1 over cosine theta. That doesn't really get us too far. We might try some things like, I don't know, substitutions, or Pythagorean identities aren't really going to work. So I think we pretty quickly realized that this is going to be a tough integral to do. And this integral, unfortunately, is one that just has a trick. It's much more fulfilling whenever you solve an integral with kind of a more deeply fundamental idea that you can learn something and then take that thing and use it in other places. For this one, there's just a trick, and this isn't a trick that I don't think that I would have come up with if I didn't hadn't heard about it. And when you come up with this trick, I don't think that at least I haven't found any other examples where basically the same trick applies. That's kind of the difference between a trick and a technique. A trick is something that like solves one very specific problem that a person typically wouldn't think of. A technique is something that solves one problem, but that can be easily generalized to a wide class of problems. So this is more along the lines of a trick. We'll start by writing this as integral 1 over cos theta d theta, and we'll multiply top and bottom by 1 plus sine theta. Why does this work? Well, it works because it works, right? As far as I know, there's nothing deeper behind this. Maybe there is some reason that that somebody did some analysis and thought that 1 plus sine theta would be a good thing to multiply by here. If that's the case, I don't know that, but as far as I know, it's just somebody figured this out. We're going to take the 1 and the 1 plus sine theta and use Pythagorean identity. 1 is cos squared theta plus sine squared theta. And then in the numerator, we note that we have some terms with sines and one term with cosines. We're going to split this fraction apart into 2 fractions and into 2 integrals. Now, sine squared theta plus sine theta is sine theta times sine theta plus 1. You might see where this is going now. Oh, I missed my cos theta. There we go. And now I have some nice cancellation. These bits cancel over here, and one of these cosine powers cancels with that one. And nicely enough, now just the basic substitution works. So if I do u equals 1 plus sine theta, du equals cos theta d theta, this is just a log. So log absolute 1 plus sine theta. Right? If I differentiate that, I get 1 over 1 plus sine theta. The derivative of sine theta is positive cos theta, so everything works out with the constants and signs and everything. And the second bit is going to be like a log absolute cos theta. If I differentiate this, I get 1 over cos theta. Derivative is negative sine theta, so I need a negative to fix that. And then plus c. Or I can use a log rule here. The difference of the logs is the log of the quotient. And lastly, I can do I can rewrite this in the way that it's often written. 1 over cos theta is secant theta. Sine over cos is tan theta. So we have log of secant plus tan. Right. Not the prettiest result, but it is what it is. Okay. So that's what this integral turns out to be. And what does this tell me? This tells me that I equals 1 over 2 root 3 times secant theta tangent theta plus log absolute secant theta plus tan theta plus c. And that's our answer. And the very last thing we should do to just kind of, fully bring this home. We really were asked the question in X. We probably should translate this back to X. That seems at first glance like that's going to be a huge pain, but it's actually not so bad, right? Well, X is just 1 over root 3 tan theta. Tan theta is just root 3x. And what else do we need? So we need tan theta. We also need secant theta. What is secant theta? Trying to find it up here. I know I wrote it somewhere. Here. X squared turns out to be, sorry, 1 plus 3x squared turns out to be secant squared, right? Secant just turns out to be this bit here, right? That was what turned into the secant theta down here. So it's just square root of 1 plus 3x squared. And then tan theta was root 3 times x, I think. Yep. All right, so to completely bring this home, we have secant theta times tan theta plus log absolute value of secant theta plus tan theta plus c. Really be ashamed to forget our plus c after all that. And that is our final answer. And that wraps up our supplemental video for section 7.2 and 7.3. All right, I will see you in class this coming Monday.